Hello, today I'll be going over some of the background of Cellular Automata, some of the ways that you can actually use it, and then a basic implementation of a Cellular Automata model. So before we begin, let's go over what Cellular Automata actually is. So the concept was discovered in the 40s by Ullmann von Neumann, and it's a model consisting of a grid of cells where the behavior of each cell is determined by what's around it, aka its environment. Now, despite this inherent simplicity, you can actually use this to create complicated patterns by chaining them together. For example, on the right here, despite the simplicity of Conway's Game of Life, which is what that is based off of, you can use it to create these machines that create these little blobs that move across the screen. Now, this concept applies to a lot of things in the world, like the computer that the simulations run on, or the human body, to name a couple examples. And it's also really great for gameplay because players can combine these simple mechanics and enable their creativity in something called emerging gameplay. Now, in most cases, cellular automata models just have cells check what's directly adjacent to them, but you can get more complicated than that if you'd like. Alright, with that out of the way, let's go over some important terms as well. So first of all, you have the grid, which is an array of cells that tracks each of their states. Now, most implementations use either a 2D grid or a 3D grid that's pretty shallow, so it only has like a few layers in the third dimension. Although I have seen implementations that use a 1D array as well. Now, inside that grid, at every position you have a cell, which is just the single unit on that grid. Now, its behavior, like I said before, is determined by environmental factors like what's around it, or its temperature, or anything like that. Now, you might also hear the term discrete come up, and that basically refers to things that are separate and distinct. So, when you look at a grid of cells, each cell is just one whole cell. You can't divide it into a half cell or a quarter cell or anything like that. So when you refer to a position on a grid, you can only use whole numbers. That's what the term discrete is referring to. Alright, now that you have a basic understanding of cellular automata, let's move on to some popular examples of how it's used. The first example is actually one that you saw on the second slide, which is Conway's Game of Life. It was created in the 70s by John Conway and has been widely studied in math and computer science, and is probably one of the most popular cellular automata models available. The whole thing is pretty simple. Cells can only have two states, with them being either dead or alive, and the way that they change their state depends on how many neighbors they have that are also alive. Now, this is actually an incredibly powerful model, again, despite its inherent simplicity, and you can use it to do pretty much anything. For example, people have used it to make computers, and people have even simulated Conway's Game of Life within Conway's Game of Life itself, which allows for infinite recursion. You can actually see that on the left here, the bottom left picture, you can see a couple giant cells being made of a lot of smaller cells. Now, there's many different ways to implement this model. Usually, people either update them on the CPU or they do it in parallel on the GPU, but multi-threading is possible on both and relatively straightforward. The next example is the Powder Toy, which is an open source video game created in 2008. It's one of the most popular games in the Falling Sand subgenre, and if you haven't heard of it before, it's basically an advanced cellular automata model where each cell has an associated material. So for example, if a cell is considered water, then it might turn into steam when it gets hot, or it'll turn into salt water when it contacts salt. Now this game actually simulates nearly 200 materials and a lot of physical phenomena like air pressure, velocity, and Newtonian gravity. The aim of the game is to be kind of a somewhat realistic simulation, and to allow players to build and experiment and just see what they can do. Interestingly, the game runs entirely on a single CPU thread, which is impressive considering the scale of the map and the complexity of the simulation. The last major example I'd like to highlight is a roguelike game called Noita, released in 2020. Here, it uses cellular automata to simulate all the pixels in the environment around the player, which is used by the gameplay to create danger, allow the player to combine materials to make new ones, or allow the player to shield themselves from danger. This contributes to a very dynamic feeling world where nothing is left the same after the player goes through. Now, some materials can actually be broken up into big physical chunks that are actually simulated in the world as well. For example, the minecart in the top image there, it's in the top left if you can't see it, it's actually simulated pixel by pixel, but the whole thing moves around as a single unit. This is pretty unique and not really seen in many other cellular automata simulations. Now, interestingly, the cells here are also updated on the CPU, but in parallel using a checkerboard pattern. I'd also like to bring up a few honorable mentions, stuff like Minecraft, where they use it to move blocks around, or map generation, like you can use it to make biomes, for example, and other such things like forest fire simulation, fluid dynamics, and stuff like that. Alright, so now I'm going to move on into the technical details of how cellular automata works under the hood. So the first basic concept is a tick, which is just a single moment in time where all the cells in the grid get updated. Then you have the tick rate, which is the amount of time between ticks, aka how often the map gets updated. So when you update the map, there are two ways that you can do it. You can either use single buffering or double buffering. Double buffering is more accurate, but each has their pros and cons. So with double buffering, you save two versions of the grid in memory. When you update the map, you look at the first grid and then translate those changes into the second grid. This ensures that any changes you make in between updates don't affect the original data, hence why it's more accurate. Now, before the tick takes place, the system will actually clear the first grid and then swap them. So that means every other tick, the other grid gets used. Now this allows you to easily multi-thread, as you can have one thread render the first buffer while the other thread updates the second. There are a couple issues though, mainly that the system has to consider the state of particles in both buffers in order to prevent cells from overwriting each other. Like for example, if you have two cells that are trying to move into the same area, with a bad double buffering implementation, one cell might move into the area and then the other cell will move into the area, but because they can't see the future state, one cell overwrites the other. That's why you need to look in both buffers. It's also worth noting that clearing the first buffer each tick takes time, and depending on the size of your map, that could take quite a while. And of course, it does use twice as much memory as single buffering would. Now, single buffering on paper can actually be faster and simpler to implement compared to double buffering. Here, you just have one version of the grid stored in memory, and when the grid gets updated, the cells are kind of updated in place, rather than copying their new states to a second buffer. This makes the implementation a lot more straightforward, and it naturally solves the overwriting problem I mentioned before, and it's actually faster than double buffering for a single-threaded implementation because you don't have to clear the second buffer every time. There are a couple notable issues though, mainly that rendering has to take place after the cells are updated, otherwise you might get visual problems. And the order in which cells are updated can influence their behavior since changes are immediately reflected in the grid. Now, in order to update a grid multiple times per second, it often requires you to push a lot of data around in memory. This makes it a prime target for parallelization, where you can actually update the cells together at the same time, rather than doing it sequentially. Now, you can either do this by processing each cell individually, or you can group them into chunks, which we'll talk a little bit more about later. Many cellular automatas use these concepts, and they either parallelize it on the CPU or the GPU. Now, the GPU is preferred for simpler models with fewer rules, and the CPU is preferred for more complex models with a lot of branching logic. In general, it's easier to write code for the CPU because you don't have to learn a shader language in order to use it, and you don't need to worry about transferring data to and from the GPU and the CPU. Now, parallelization and optimization in general is easiest when cell behaviors are constrained. So keep in mind that the more freedom and power you give to a cell, the harder it's going to be to optimize later. So two important concepts in optimizing a cellular automata model are chunking and sleeping. With chunking, you take the grid and divide it into smaller pieces called chunks, which each track the state of the cells that they contain. If all the cells in a chunk can't change their states anymore, then the chunk will tell the system to put itself to sleep, and it will inevitably wake back up when any cells on its border in the adjacent chunks try to perform data-changing actions. Now, the reason why this helps optimize the game is because when you're updating the map, you can skip the sleeping chunks, which can save a lot of processing time, especially if they're filled with particles or cells that don't really do anything, like air particles, for example. Sleeping chunks can also render their cells to a canvas and cache the results in memory, so they don't need to be re-rendered every single frame. And these techniques can also be combined with stuff like quad trees or dirty rectangles to optimize them even further. Alright, now that you understand some of the technical concepts behind a cellular automata model, let's go over the implementation of how you can make one for yourself. So the model we'll be implementing today is fairly straightforward. It's a single buffered 2D falling sand simulation. The reason why we're doing this is because it's simple enough to demonstrate the concepts of cellular automata, and it can be modified to emulate practically any cellular automata model. We'll also be doing this in Love2D with Lua. I did this because Love2D has a very simple API, and Lua is a very easy to understand language. The only pitfall of Lua you need to be aware of is that arrays start at 1 and not 0, so when you're translating it to your own language, make sure you're aware of that. So to begin, all we need to do is create a reset grid function to actually create the grid itself. Now inside that function you're going to need 2 for loops, one for each dimension. At each x position you will want to create an empty array, and then at each y position you'll want to create a tile object with an attribute named material. And for each of those, just set the material attribute to air. Alright, so from here on out, after each of these slides, I'm going to show you how you can implement it in Love2D. So right here, you can see I'm highlighting the reset grid function, and it's just like I said. You create the grid starting here, and then for each x position, which is this for loop, you create an empty array. Then for each y position, you create a cell with the material set to air. Alright, with that out of the way, now we can begin working on the update logic. You'll want to start by making another function with 2 for loops again, and in the innermost loop, you'll need to check the material of the cell and then find and run the corresponding update function. Now here you can actually see the update grid function that I made, and like I said, it just has 2 for loops. Inside of it, we get the cell, then we look up the cell's material, use that to index the materials table, and then run the associated update function. You can see we're also passing the grid size, and the location of the cell to this function as well. Now inside your update loop for your game engine, what you're going to want to do is create a variable that'll track the amount of time since the map was last updated. Here you can see I've made a variable called last tick, and every single time the update loop runs, we're going to add the delta time to that. Then we check if it's greater than the tick rate, and then update the grid inside of this if statement. Alright, now we'll move on to the grid rendering logic. Here you'll create a pretty similar function with 2 for loops, except inside the innermost loop you'll check the material of the cell to get its color, and then render a square to the screen. Alright, so here you can see the render grid function. Like the update grid function, it's very similar. You have 2 for loops, you get the cell, you index the materials table to get the cell color, and then you render a rectangle. Now the key difference here is that inside the game engine's draw loop, you actually run this function every single frame instead of every single tick. Now that we've done the legwork of actually defining the underlying model, we can start defining some materials to exist in the model. The first one we'll do is air, which isn't really going to do much aside from take up the empty space in the grid. Alright, so we're now in a new file, and you can see up here I've defined this materials table, where we're going to store the information for each material we want to make. The first one was air, so we define it like so, where we give it a color of light blue, and then we give it an update function. Now you'll notice that this update function doesn't actually do anything, and like I said, that is because air is just meant to fill in the empty space in the grid. The next material we're going to define is sand, which is a little bit more complicated than air. Unlike air, sand is affected by gravity, so it needs to go downward whenever there's empty space below it. So you can see that we're back in the materials file, and I've defined a material called sand with a color of yellow and a slightly more complicated update function. This update function simply checks if the cell below it is an air particle. If it is, then it swaps the 2 cells in the grid. Now, one thing to keep in mind is that down in the grid means adding 1, not subtracting 1 like you might expect. That's mainly due to the way that the game engine renders the cells, because it starts from the upper left corner of the screen and then goes down to the bottom right, rather than going from the bottom right to the upper left. Alright, so here you can see the results of our work. This is the first version of our Cellular Automata model, and here you can see the full code for it. Here's all of our functions, here's our update loop, rendering, and then this just resets the grid. Very straightforward. So now that we have a basic version of our Cellular Automata model, we can start working on map interaction to allow us to place stuff in the grid itself. To do this, we'll need to create a function that can translate screen coordinates to grid coordinates. Usually you'll do this by just reversing the math you use in the rendering loop. We'll also need to track when the player is holding down the mouse button in the update loop. Alright, so now we're back in a new version of our model. Here you can see I've added a screen to grid function that takes a screen X and Y position, uses some math to translate it to a grid X and Y, and then returns the pair of values. Inside the update loop, we get the mouse position, feed it to the screen to grid function, get the map positions, check whether the positions are actually in the bounds of the grid. Then we look at what mouse button is held down. If the left mouse button is held down, we replace the tile with sand. If the right mouse button is held down, we replace it with air, effectively deleting the tile. So here's the new version of our model. You can see that I've added a grid so you can more easily see where you're placing the particles, but there's just one small issue. When we try to place sand particles, they actually teleport to the bottom of the map. This is one of the issues I mentioned with this single buffered implementation. Because we're updating the grid from the top left to the bottom right, when we place a sand particle, the system will iterate over its row and move it downward. But then the system will move down to the next row and iterate over it again, and it'll repeat this process until the sand particle is at the bottom of the grid. Now, in real time, it just looks like the sand particle teleported all the way to the bottom. So I'm going to demonstrate visually what I mean with my mouse. Let's say I place a sand tile right here. Now, the game is going to start updating starting from this top left corner, moving right, going row by row. Eventually, it'll reach where the sand tile is and update it, moving it down. Now, the system's going to keep updating this row and then move on to the next row, where we just move the sand tile. When it reaches it, it's going to update it again, moving it down another row. Then it'll keep updating the tiles in this row, move down another row, and update the sand tile again and again and again, until it reaches the bottom of the grid. So there's a couple ways we can solve this. The easiest is to give each cell a Boolean attribute that tracks whether it's been updated in the current game tick. Before each game tick, all of the cells in the grid will have that attribute set to false. Then, when a cell is updated by the update function, that cell's attribute will get set back to true. If the update function ever comes across a cell that already has its attribute set to true, then it'll just skip it. Now this method has a big disadvantage in that you have to iterate over the entire grid twice. Once to update each of the cells, and then another time to set each of those attributes back to false. A more efficient way to implement this would be to track the system time instead of a Boolean flag. At the start of each tick, you'll want to record the current system time. Then when a cell gets updated, instead of setting that attribute to true, we set it to the system time. In this case, we'll be updating any cells that have a system time older than the current. So now we're on the third version of our model, and you can see that I've changed the update grid function a little bit. At the start of the function, we get the current time. Then we check each cell's last update. If it's older than the current time, we update it. If it's not, then we just skip it. Pretty straightforward. Now with these changes implemented, our sand particles fall just like we'd expect them to. And that's about it for the first basic Cellular Automata model. But there's a few more improvements that you can make if you'd like to enable more complicated behavior. Alright, so in this next section, I'll be going over a couple more examples showing you how to implement higher level features like more materials or how to better organize your project. So the first thing I'd recommend you do is to design a map manager to handle all the map interactions and updating. This will not only provide a standard way of reading and writing data to your grid, but it allows for easier scripting, keeps your code clean, and makes modifications a cinch. Some examples for things you should add would be stuff like adjacent cell movement, movement in straight lines, performing actions in a radius, or spawning cells in a grid. So now back in the code, you can see that I have made a fourth version of the model, except this time I have imported a grid manager. Now this basically does the same thing as our code before, except now everything's packaged inside one object. So you can see here we initiate the map, then down here we do the updating, down here we do the rendering, and you can see here instead of manually checking whether the grid position is valid, we use a function for it. And the same thing for replacing tiles in the grid. Inside the grid manager here, you can see that we store the grid inside of this grid manager object, alongside the grid size and the cell size. We also have the materials here, which we'll keep a reference to, and this gets initialized in the init function. Then down here, we just have the reset grid, update grid, render grid, all the functions that we had created previously. The syntax is a little bit different because now we can reference self instead of the grid object. And I've also added a few more methods down here, like get material, replace, swap, and validate. The code for this should be pretty self-explanatory, but take a moment to pause if you're interested. So inside the new materials file, you can see that we import the grid manager, and this makes our lives a lot easier because now we don't have to rewrite so much code or do so much stuff manually. So before we were manually checking the positions to see if it was air. Now we can just use this method for it. The same goes for swapping the tiles. We just call a method for it. You can see how this is a lot more simple and clean than just doing it manually. Next, I'm going to go over a few concepts you can add to your falling sand simulator in order to give your cells more complex behavior. First thing you can do is allow powders to form piles. You can do this by detecting when a cell stops falling and then making it move either left or right. You can also give it a chance to not move at all, and the higher the chance, the taller the piles will be. Another thing you can do is make liquids spread out by moving them left and right randomly. Now you can use RNG to change how often this occurs to give the impression that a liquid is thicker or thinner. For example, if it has a low chance to move left or right, then it'll appear thicker. If it has a high chance, then it'll appear thinner. It's not the most realistic way of doing this, but it's fairly cheap to compute and very easy to implement. Another surefire way to increase the complexity of the model is to add temperature, because this allows for a lot of different stuff, such as changing a state depending on how hot a material is, or allowing it to combust. You can also use it to simulate things like electrical or thermal conductivity. And finally, you can implement a velocity system to move particles around the grid rather than manually doing it inside each of their scripts. Finally, before I go, I'd like to go over a few of my own implementations of Cellular Automata. The first is just another sand game, which I've been working on and off since 2022. It's a falling sand game that emulates the behaviors of over 300 materials, and it uses simple material properties to create emerging gameplay, which is meant to incentivize the player to experiment with the particles and exploit their interactions. The other example I want to highlight is Depths of the Powder Fields, which is a little wave-based survival game I made for a jam a few years ago. The basic idea behind it is that players need to build their weapons after each wave pixel by pixel. Then when they hit something with the weapon, damage is simulated to it via Cellular Automata. Players have to consider the properties of the materials they use and the shape of the weapon because it affects the end damage. Using heavy materials will make the weapon swing slower and harder. Using sharp materials like metals versus soft materials like bones will also make the weapon do more damage. And if you use a serrated pattern versus a flat pattern, it'll do serrated damage versus sharp damage. So here you can see just another sand game, and in the background there's actually a map playing out. This is a 4-cylinder gasoline engine that's powering some electrical shields. Now I can actually go into the map and view it, and you can see that there's a variety of materials here, and some of them have interactions that might be interesting. So like, let's say water and salt. We can combine those and make salt water. You'll also notice that the water is getting absorbed by the dirt and turning it into mud. Now if we keep adding water, it'll turn to salt water, and you can see that the heat of the engine is actually heating up the salt water and then separating it into steam and salt particles once more. Now this implementation is a lot more complex than what we just went over. Here you can see the map manager that I made, and there's quite a lot of functions here. Most of these are used for either moving particles around the map or transforming them in some way. This one, for example, transmutes a particle. You can also see that our update loop is a lot more complicated as well. In this code it's called the act phase, but it's the same concept. Now this simulation actually has 2 layers, so technically it's 3D. But yeah, that's why you have these 3 loops here. And then inside of here we're doing the temperature calculations, more temperature calculations, chunk sleeping. Here we're detecting if it's dead. And then here we do all the velocity calculations. And then here we actually call the update function for it. So here is depths of the powder fields. On the right hand side here you can see our weapon simulation. Now this red area is the part that we actually hit enemies with. And we can place materials in here. So if we do just a flat design, it'll just give us sharp damage. But if we alternate it, it'll give us serrated damage. And of course, the weight of the weapon also determines how fast it is to swing. So for example, I'm holding the button right now and I swing at about this rate. If I delete all the metal, I'll swing a lot faster. Now to show you what this looks like in the wave, it's pretty basic, it was just made for a game jam, but you get the point. I better add some materials here so I can actually defend myself. But yeah, you can mine these blocks to gather more materials, and the materials you use also interact with the cellular automata system. So for example, Alnium can rust over time, so eventually, like right there, it'll turn brown and might fall off the weapon. So diving into the code here, you can see that this simulation is actually not much more complicated than the one we implemented earlier. We have the basic functions you'd expect, like clear, spawn, delete, etc. But scrolling down, you can see these damage functions. These are what are used to simulate damage on the weapon whenever you hit something. So this one does horizontal damage, this one is vertical pattern, this one is a circle pattern, and this one does an X shape. Now these are all used inside the calc damage function to apply one of these patterns at random whenever you hit something. So yeah, that's it for now. Thanks for watching, and I hope this tutorial helped you.